Hello, everyone, and welcome to phyloseminar.org. The current theme is machine learning for the second time, and this is the fifth talk in a series of 5 talks on that topic. Please use the YouTube live comment box to ask questions. Today's speaker is Dr. Samir Bhatt. Samir is professor of machine learning and public health at the University of Copenhagen and a professor of statistics and public health at Imperial College London. Samir has a diverse range of interests, but is currently enjoying working in branching processes, phylogenetics, image and video processing, infectious disease epidemiology, and causal inference. Welcome, Samir, and thank you for participating.
Hi all, thank you for listening. Hope you enjoy this talk. Just to let you know, I will be speaking primarily, but Matthew Penn from the University of Oxford, who's done all this work with me, and most of the ideas are his, is also on the call and may jump in if he feels the need, or may just answer questions if they come in. So the talk is methods for phylogenetic inference using gradients, and I guess we are now familiar with the deep learning revolution being underpinned by automatic differentiation and this ability to optimize functions by their gradients, either doing a first order method or a second order method. And so the idea, is quite logical. Well, what how do we apply this to phylogenetics? And of course, it's not an easy problem because of the discreteness of phylogenetic inference. And so there has been excellent work out there already applying gradient-based inference, work from Mark Suchard and others, showing how you can calculate gradients for branch lengths. But our central focus is this idea of topology. Right now, most will know this problem, which is for phylogenetic trees, this space is absolutely vast. Right? It's I'm fond of saying this, but if you just take a phylogenetic tree of 30 people, and you wanted to count the possible trees, and how would you count? Well, let's say we count each tree as a hydrogen atom. That would form a star. So the space is unbelievably vast, and we're never going to be able to search it. And most of the objective criteria for what is the best phylogenetic tree are NP-hard problems. And so if we see the vastness of tree space, we see the plot over there has the black line as the double factorial, which is, it's not what you might think is a double factorial. It is that product up there. The blue line is the factorial, and for reference, the red line is the exponential. I put these up here because we're going to be referencing them in a little bit. So I guess the first question that we had to tackle when we wanted to try to make some progress on this gradient question was, well, how do we represent a tree? Now, everyone who's worked in phylogenetics will know about the New Hampshire tree format, Newick, which is this string format with A, B, C, D, E, taxa, and the parentheses and the commas help specify the topology, and then we can extend this by adding branch lengths and bootstrap support and all these different approaches that we can put in. And so, you have different examples of how you can construct Newick trees together. Just to note, the text up there and the tree down there aren't magic. But of course, there are many other ways to represent a tree. And I think the most, one of the oldest and perhaps really widely used one is the proof of sequence or the proof of codes, where we sort of iteratively take away branches until we're just left with 2, and we end up with a code that can be processed in linear time. Now, proof of sequences are extremely powerful and have been used throughout a wide range of computer science tasks. They can be processed in linear time. So they're extremely efficient. And they do provide this idea of this integer encoding, right? That, okay, well, representing a tree as a series of strings, it makes life very difficult to do deep learning and computer science with it, right? How do we sample random trees, right? We'd have to construct that string. It would require lots and lots of constraints. This makes it very, very challenging. For a proof of sequence, we just have this integer and an algorithm that could end up constructing it. Now, of course, the proof of sequence is more general than for binary trees. It's for any tree, as you can see there. But if you look at A and B, you can see that just changing the first index from 2 to 1 creates quite a big change in the tree. And I'll get back to that in a second. Another example, just to sort of overview some of the previous examples in the literature, there are a lot more of this, and I can't do justice to all the methods out there. Are matches by Daconis and Holmes. Matchings look a little bit like Neweg strings, but all they are essentially is a permutation. You create a vector of permutations, and it tells you which pairs you match up together. And in the paper, which is worth reading and very short, although missing some details, which I wish they had when on first reading, you can see the construction is rather simple. You just keep pairing together. You take 1 and 2, create a new node. 3 and 4, you keep pairing as such. So this immediately starts an interesting idea. Well, all right. Well, if we have permutations, then that's a simple way to encode a tree. And that's actually how Matt and I first started on this. We sort of thought, well, Daconis Holmes, matchings, let's just do this and get gradients. And we're both from different backgrounds, and so you'll have to forgive us for not understanding the complexity in all of this. But we've learned it as we've gone by, which is why do we need another encoding, right? Why can't we use these? Why can't we use what we already have? And I guess the question really is, what makes gradient-based topology changes hard? So the first thing is we have to be able to continuously represent a tree. Right? So maybe with the permutations, we could create a matrix that's softmaxable and put a constraint such that it's a valid permutation. But that's not the only thing that we need. We also need the gradient on this tree to be in some sense smooth. Now, for matchings and for proof of codes, a small change in the integer representation can create a humongous change in the tree. And this makes it very difficult to take small gradient steps, or indeed just to do hill climbing, because you can end up with very big changes in the tree that you don't necessarily want. So I say in some sense smooth. And the other one, which of course we completely undervalued, was we need the objective function to also be continuous. So to take examples on the matchings are permutations. So, my colleague Gonzalo Mena has done lots of interesting work on the Gumbel sinkhorn method. Take, for example, we're going to use the Gumbel sinkhorn, and that's a differentiable way of sampling permutations. Cool. So we could use matchings, but now we need to actually calculate the gradient on the reconstruction step of the tree. Because if we're using Felsenstein's likelihood, we need to do some post-order tree traversal on a tree and then calculate the gradient across that. And so we have this discrete step in first, the encoding, second, the reconstruction of the tree, and then third, in something like Felsenstein's likelihood, or the phylogenetic likelihood, where we actually need the discrete tree to take steps over. And if we are going to do this in the classic mathematical way, we need to be taking expectations over some continuous relaxation. And as we quickly learned, that makes life very, very difficult. So the idea we had was we need to keep this integer encoding as simple as possible. And of course, the easiest way to do this is just by choosing a softmax without even the permutation constraint, right? And so our representation, just to go into some of the details, and of course, I realize this is notation heavy, but I'll explain it as best as I can. In our representation, we have n taxa, and so we have k integers. And so we can create this vector of k integers. We have a very, very simple constraint, which is the constraint written there, that we can map on such that at any index I, you can take any integer from 0 to 2i. So it kind of gives you this sort of lower triangular or upper triangular, depending the way you're thinking of it, matrix, from which you can simply take a softmax. And for those not familiar with the softmax, it's just the logit in with multiple categories. You can just take the softmax, and then that gives us a unique tree, right? And so the idea was, if we start from this simple representation, then we know that the softmax has been used regularly to pass gradients through. That's a sensible way. But then what is the algorithm you use to then reconstruct the tree? Just to reassure you this makes sense, you can see that the index can go anywhere from 0 to 2i. So by definition, the number of possible unique integer vectors is actually the number of possible trees. And so by construction, our algorithm, sort of had these properties. And I can reassure you that when you're creating these integer representations, these little slip-ups happen all the time, because the first one we did, actually, it didn't match the number of possible trees, and we didn't have a bijection, and it sort of failed. So I'm going to go through the very high level algorithm of this. And essentially, we process from the leftmost node, so from the rightmost node leftwise, and we have this matrix that is the view matrix. So, to not go into the intricacies of this algorithm too much, imagine that every node calls itself something, right? So I'm node 4, I call myself node 4. I'm node 3, I call myself node 3. Every time a new label comes in the tree, I can call myself a new label, and there is an ultimate labeling at the end of it, which is the true labeling. So we create this matrix, which is the view matrix. It's the view from every single node. So if I'm node 4, I think I'm node 4. I think the node next to me is node 3. I think it's node 2. But that's my own internal labeling. And as we follow this algorithm from right to left, node can only be processed once it sees its own label, which creates a very sort of robust way to end up with an algorithmically forming the tree. And so we iteratively merge pairs as we build this tree. And the properties of this algorithm, which I highlighted in the paper, and I'll show you in the next slide what it looks like. The properties of the algorithm are, first of all, is bijective. So every unique integer vector results in a unique phylogenetic tree. And you never have an integer vector where you put that in and you get two trees out. Algorithmically, and this is actually quite challenging to do, algorithmically it's provably well defined, which is good. So we know that if we follow this algorithm, we're not going to end up with any slip-ups anywhere. When we conceived of this algorithm, because of perhaps due to the lack of experience we had, we did everything in a rooted framework, even though unrooted trees are more common in inference. So rooted and unrooted trees are possible, but this is probably a better approach for rooted trees. And then one of the really cool bits about this algorithm is this idea of, in some sense, smooth. There is a deep connection between changes in the integer vector and the popular move, which is called subtree-prune and regrafting. Sorry for the typo there. So subtree-prune and regrafting is exactly what it says. Take a subtree, chop it off, regraft it somewhere else on your tree. Now, changes in our integer vector, so for example, if I change one index in our integer vector, that corresponds to a subset of the SPR moves. And of course, I can make 2 changes, I can make 3 changes, but the idea of our sort of algorithm and its connection to subtree-prune and regrafting is very close, and we have some derivations and some proofs at the end of our paper where we discuss this. So these things, I realize that this is complicated because it's sort of, I'm trying to explain 2 papers as well, 3 possibly rapidly in this talk, and so I can't have the luxury of explaining you this algorithm very closely. And members from Eric Matson's team are already sort of looking at this, and there may be better ones coming out anyway. But take these example trees, right? So take the first one. We've got a Newick tree. 1 pairs up with 2, 3, and 0 paired together, and you have the internal nodes 4, 5, and 6, right? And you can see that the phylogenetic vector is 0, 0, 0, 0. Now, there is a nice way to think about this, which is, Matt and I came from the world of branching processes where we're doing work there. You can kind of think of this as a branching process. You can say, you start off with node 0, and then, node 0 splits, and when node 0 splits, it continues living but creates a new node 1. So at 6, we end up with a split that creates 1 and stays at 0. Then node 0 continues living and creates 2. And then node 0 continues living and creates 3. And that's one way of thinking about how this algorithm works. But of course, there are some labeling difficulties in here that means it's not as simple as that. But that was the inspiration for it. So sort of taking inspiration from branching processes. And so we using this phylogenetic vector, we can now create very simple ways of sampling and defining a vector that can then, easily be cast into a Newick tree, put into a linked list, put into software to represent a binary tree. There's many different ways of sort of handling this. So let's go through the basic advantages and disadvantages just to highlight what's good about this. Well, it's a simple integer format, which is what we really wanted. So an integer vector, very easy. It's very easy to manipulate, right? We keep this vector. We can cast it as a one-hot matrix. We can calculate distances very simply, and these distances have some sense because of the connection to SPR, subtree-prune and regrafting. Having a phylogenetic tree requires you to put in a lot of constraints because we have this binary bifurcating tree. The constraint that we have is simply trivial, right? It's one inequality, and that's it, right? Less than or equal to 2i, 0 less than or equal to 2i. And so it's trivial to sample random trees, and it is trivial to sample random trees from Deconis and Holmes and from proof of codes. But I think in some ways this is simpler because we can make small changes to the tree, and we know that they'll be small. Now, the first disadvantage is our vanilla algorithm has a time complexity which is quadratic, which is, it's okay for small trees, but it's not great. But as we show in our paper, there's actually a linear time algorithm which is possible with this ordering when we use something called ordering. And you might think about, well, what is ordering? Ordering is exactly creating a series of labels in your taxa such that you can use that nice branching process intuition that I said before to construct a tree. So you never have to sort of skip which node you're processing next. You're always processing from right to left and never having to do skips. And that way, we end up with a linear construction. So with ordering, linear time is possible, and there may be better ways of doing this. The disadvantage is no real integration to branch lengths now, in a sort of nice way to encode the branch length with the tree. But of course, you can always compare two trees and copy branch lengths from parts of the tree which haven't changed. So all the standard methods can still be used once you've created the topology. Like I said before, one way to make things much simpler is called shuffling. And by shuffling, we can always process the tree in linear time. And that's the example that I've given down there. So it keeps the exact same topology. The constraint is even simpler because now it's less than I, not less than 2i. And so it gives us this lots of flexibility to process in linear time. It's also easier to understand, right? You sort of process everything as you see it. So that's enough on the Philo-Tvec theory. What does it look like? Well, with a Philo-Tvec integer vector, we can always calculate the Hamming distance, which is just the number of indices in this Philo-Tvec vector which are different from each other. And you can see that the Philo-Tvec distance correlates pretty strongly with subtree-prune and regrafting distance, but SPR distance does saturate as Philo-Tvec gets more and more distance from each other. And so in a way, Philo-Tvec, the most simple application, which could be useful, could not be useful, I don't know, is you can get two trees, convert them to Philo-Tvec in linear time, and just calculate the Hamming distance between them. And it could be in some sense easier than Robinson's fold distance, which is very interpretable for topological accuracy, but it saturates so incredibly fast that for large trees it can be very, very difficult to sort of use. So let's take in examples, and of course, the classic example is the yeast example from Rokas in 2003. Here we took every single tree and calculated the Philo-Tvec vector for every single tree, and then we simply did hill climbing on the Philo-Tvec tree, taking steps. And you can see immediately that the steps are very, very rapid as you traverse this tree space. And this, I guess, shouldn't be too big of a surprise. I guess it was a surprise for us at the time, but in retrospect and from the things I've told you now already, it shouldn't be too big of a surprise because of the connection of Philo-Tvec to subtree-prune and regrafting. And so, the immediate application of this is Well, let's stick this into RaxML, or rather, let's use RaxML to calculate the likelihoods in the branch lengths, and let's do the topological search by phylogenetic. Let's see if we get stuck in places. Let's see if it's problematic. And we tried this for 4 data sets of varying sizes. I think, going from 20 to around 80 taxa, so nothing big, and then did 10 independent runs. And we converged to the same solution as RaxML, which is that dotted line at the bottom, in a certain number of epochs. And so, immediately you can see that this phylogenetic, it may not be more efficient. I mean, obviously the code that we have is still in its early days, and it needs to be optimized. But it does allow you to be a bit more systematic with your moves. And so in my mind, this is a particularly great match for Bayes, perhaps not for time trees, but for your standard Bayes. It's approximately subtree-prune and regraph with singular changes. But we can do lots of cool things with a random walk metropolis, right? We can change single indices randomly. We can increase the temperature and change multiple indices to make big changes and small changes. With our ordering algorithm, we can process this in linear time. It might make for an easier way to do systematic changes or systematic random walks. But of course, none of this, obviously, I want to give you all a balanced perspective of this, right? None of this isn't possible with the tools out there now. It's just a different tool for this. And so for the first 3 points, tools exist right now. It's not like we're fulfilling some great unmet need. I think one unmet need is the last point over there. Our trees are rooted, and so they could be used for non-reversal models. So there have been several papers out there, showing, I think the papers by Samir, showing that the general time reversible model has issues in the sense that it's not valid under closure when you multiply or add 2 of them. So non-reversible models, might be useful for a range of phylogenetic problems. They certainly would be more plausible, but we need a rooted tree for that because of the direction. And phylogenetic can give the tool for it. So let us just take stock there. Where are we so far? Well, we wanted to do gradients. I haven't spoken about gradients yet at all. To do that, we needed some sort of representation. So we realized, given how difficult it is to calculate gradients and where we need to calculate gradients, let's choose the simplest representation we have. In our minds, it was this softmax matrix. Okay, how do we get an algorithm to process it? And that's the contribution of phylogenetic. So now we go what about gradients? Well, we have this softmax. We know I can populate the softmax matrix with probabilities. I can take an argmax on that, or I can just keep it as a softmax matrix. I can calculate gradients down that. Perfect. Now, what about my objective function? So Matt and I tried doing this in Fels's likelihood, and we just simply could not get it to work. And so we chose an easier, but also very interesting framework, which is that of balanced minimum evolution. Now, there's a great paper by Daniel Catanzaro on a tutorial to balanced minimum evolution. It's a really phenomenal paper to read. I recommend everyone reads it. And in summary, balanced minimum evolution is the criteria for the neighbor joining algorithm. So neighbor joining is a heuristic algorithm for balanced minimum evolution. And balanced minimum evolution, its idea is we want the tree, if we knew the true distances, the true evolutionary distances between pairs of taxa or between all taxa, the true tree will be the tree with the minimum length. And some work done in the 2000s and some seminal work by Olivier Gaskell and Richard Desper, sort of set the foundations for balanced minimum evolution. Now, balanced minimum evolution is nice because you take a distance matrix and then you encode all you need to know about your topology by the path length, so the number of edges connecting one taxa to the other. So if 2 taxa are sort of cherries, then they're connected just by two edges. You don't really care about the length of those edges. And so this makes life, again, easier because we're dealing only with topology. Branch length becomes a problem that you do later on. And so in this framework, Matt managed to find out a nice algorithm that you could calculate the expectation across our softmax matrix W. So in the first line there, W, that's our softmax matrix. We want to calculate the expectation with respect to some objective function. Balanced minimal evolution is the product of a distance by 2 times the power of the path matrix. We found a way to calculate the expectation across that, such that we would end up being able to pass gradients all the way from the softmax to the objective function, and then find the best tree. And algorithmically, it's really, really simple. So that's the algorithm I have down there. It's super simple to compute. Of course, you can see one big problem, or I mean, it depends how you view it. We sort of just had this under review, and one of the complaints was it's cubic, which isn't great, because most algorithms out there would be quadratic. But I'll discuss this in a second. And in code, of course, this is just some Python NumPy code. It's really simple to code up, and of course, it just mirrors the algorithm I've written there. But sometimes for people doing phylogenetics, it's nicer just to see this NumPy code and think to yourself, well, I could just go and write my code right now and do this, and that's all. You can sort of code this up very simply, and as I'll talk later, look, the simplicity of this means we can actually port this to the state-of-the-art software like JAX to do automatic differentiation.
So Samir, can you go back and is this the gradient? Before you showed us results, were you comparing to Raximo and so on about a gradient based? Yes, yeah. This in the previous slide as well. So is this
this is what the discrete gradient or the hill climbing. So this is simply in a phylogenetic, pick an index in the phylogenetic vector and try out all the possible changes that you could for that index and iterate.
Perfect. Great.
And so the dotted vertical lines are epochs. So that means if you reach the dotted vertical line, you've done every index once. So 2 epochs, you've done 2 passes of the vector. It's reasonably fast, but this, again, we know this because we know subtree-prune and regrafting is quite efficient at exploring space.
I wonder if it would have you ever thought about taking looking at the grade, the top couple of DME gradients, and then evaluating the likelihood
so
for each one of those, and doing sort of a hybrid where you would be using the BME to suggest good SPRs and then evaluating them.
Yeah, so this is exactly what I've been thinking about this week after looking up at the RaxML paper. So their fast SPRs does this. Again, work from Olivier Gaskell back in 2004. Yeah, I will discuss this in a second, actually, as a possible application. So we have our expectations, simple code, but it's cubic, right? Not great. So just to give you some intuition of why this might be useful, and once again, why we might want to do exactly what Eric just said. So the top is the matrix that we would have, that softmax matrix. So the reds are the zeros, and if it's 1, it's green, and numbers in between 0 and 1 as you do in your softmax are somewhere in between. So the top matrix, this can represent, I'm going to be loose here, but this can represent every single tree. In truth, it can represent a factorial number of trees for reasons I'm going to go into in a second. But when you're doing things discretely, like in that second argmax matrix there, some indices are 0. You can't suddenly move from those indices somewhere else. Whereas you can do this in the continuous matrix. And so this is why the continuous matrix, we call it leaping through tree space, because it can explore almost there's a unique path between every possible or a factorial number of trees via this softmax matrix in a way that you could not do once you discretize the problem. And so this sort of gets around the idea of getting stuck in local optima. So if you get stuck somewhere where no SPR move will get you out, that doesn't mean there's a better tree. It just means that, maybe you needed 2 SPR moves. And that's where the continuous representation is useful. And so, yes, doing subtree-prune and regrafts, and every single one, looking at every single subtree-prune and regraft is a quadratic operation, n squared. And calculating our gradient is cubic. you do get something from that, right? It's not that we are just doing something more expensive. We do get something from that. And so the properties of this whole
So sorry, can I just interrupt you one more time? I have looked at this figure in detail and I understand what's going on. I don't think that necessarily everybody else watching. Can you just explain a little bit more about, I mean, you talked about softmax. I understand there's a continuous parameterization. Can you just say a little bit more about what is getting softmaxed?
Yeah, so it's the rows. So the rows are getting softmax. So if you look at rows, this is a 10. I think it's just some random matrix I created, but it looks like it's a 10 taxa tree. So you need 9 integers to represent it. We say that label 1 or taxon 1 gets an integer 1, taxon 2 gets an integer 2, taxon 3 gets an integer 2, taxon 4 gets an integer 1, and so on. So this then gives you your phylogenetic vector from which you can reconstruct a tree. That's in the discrete sense. In the continuous sense, every possible tree is possible there. It needs to become discrete for you to then, sort of evaluate a tree. But as I was getting to here just in a second, apart from Banff's minimum evolution being consistent and the objective being continuous, when you run our algorithm here on this gradient, we always end up in an optimum that is discrete, provably. So we start from this continuous matrix, we take gradient steps in this continuous space until we get to the best tree, which is always discrete. And so we end up with a discrete tree at the bottom. So for those thinking out there, in a very real sense, the continuous space is representing every tree at once and sort of looking at all the various probabilities, and then we take an expectation across that. And that's why you need to take an expectation to do gradients. And we can do some nice things on routing and reordering. So I know I'm conscious of time and conscious of all of this being incredibly technical. I'm sorry for that. But I just want to talk a little bit about shuffling. So there is something negative about all these algorithms, right? This algorithm requires our phylogenetic vector to be ordered. And so this only gives us access to a subset of all the possible trees. So it gives us access to that blue line over there. But the true number of trees is the black line. Now, I've written out an analogy that might make sense to others in there. So finding the best tree in the black line is akin to finding a needle in a haystack. So what we do is we search through many, many big stacks of factorial number of trees. We search through many of the blue lines. So in truth, it's a much bigger haystack. But we have this gradient, which is like a magnet that allows us to find the needle. And the needle is now no longer just in one big haystack. It's in these other haystacks, and you have many of the needles in there. So this is, in computer science parlance, enlarging our problem space, but finding a better way or a more efficient way to search it. And that's what we do here. And one of the really nice parts of this, which is, I think we haven't communicated well enough, is something called Q shuffle, which is a means of transitioning between one haystack and another haystack. And Q shuffling means that we don't, the probability is constant, so we never really need to scale by the number of taxa. We never get limited by the number of taxa. We can always find a haystack that has a very good number of trees in it after searching one haystack. I realize this is sort of technical and hard to explain in the number of time, but long story short, we create an algorithm that can search through gradients on a factorially large number of trees. But the true space of trees is a double factorial. So simply by reshuffling the labels, we can explore a new factorial range of trees. And we can do this extremely efficiently. And so taken all together, this allows us to use the gradient to rapidly explore space. Now, I guess after all that maths, a picture helps encode it much more. So, you start off with the matrix on the very far left hand. That's our softmax matrix for, the famous PAML primates problem. We calculate the gradient, and then all I've done is, take the original matrix plus some step size on the gradient and then produce the argmax tree. And you can see in one step, we go from a nonsense random tree to the correct tree, which is, a leap of 6 subtree-prune and regrafts. So if you were doing this in a classical piece of software, you'd have to search through, n squared subtree-prune and regrafts and do that 6 times to get to this tree. And
Maybe
I think
you could explain that in terms of the bundles. I mean, just to connect.
yeah. So the true phylogenetic representation should have 24 rows, or sorry, 24 columns, right? But to ensure that we can calculate the gradients, we have to restrict it to 12. So we only ever if you think of phylogenetic as pairing together, we think of these bundles as trying to pair together leaf nodes only, and shuffling labels as a means to access internal nodes. Maybe that's a nice way of thinking about it. I don't know if that sort of explains things better to you, Eric. Or,
Well, let's see. So there's a shuffling that's associated with each of these trees, I think.
Well, no, because what we're saying is that we can use the gradient to explore the space of these trees, but that space is not the true space of all possible trees. How do we access the true space of all possible trees? We can simply shuffle the labels.
So these two trees share a given shuffling.
They share a given shuffling, yeah.
And but the gradient allows us to, like, within that shuffle, condition on that shuffle, sort of.
Yeah, and I'm very glad you brought that up, because that actually explains things better. You don't need, there are exponentially large number of label shuffles that can give you that exact same tree. You don't need to find the perfect shuffling. There are exponentially different ways of getting that tree. And hence the whole, there are many needles in many haystacks. You're not sort of searching for the perfect shuffling, right? Yeah.
Cool. Thanks. It's amazing.
Yeah, it's a big step, and in terms of you could, but well, I'll tell you the negatives in a second. But so the cool thing is you can use modern machine learning tools. So you can write this as a function in JAX, which is an amazing bit of software. JAX will do the automatic differentiation for you. It'll do it all on GPUs. So you can do some very fast ML with this, rather than having to write your own C code, which is difficult. Empirically, I'm conscious of time and we have a lot to go through. So empirically, it's pretty good. The take home from this one is FastMe is an amazing bit of software. FastMe uses SPR changes. FastMe doesn't always find the best tree. In some cases, ours does. And so, if we could do an algorithm like this for maximum likelihood approaches, I think we would be able to explore space a bit better. I'm going to touch on this a little bit now, but not dwell on it too much. One of the nice results we found, which to our knowledge we haven't seen before, is in balanced minimum evolution. If you pretend that you have an ancestor that's very distant to all your taxa, you have an ultrametric tree, you can estimate the tree and the root. So using our algorithm, we can estimate the tree and the root. And so this plot here is simulating ultrametric trees and adding noise to them. And if you add no noise, then our algorithm can always find the right tree and the right root, with the correct model specification, whereas midpoint routing, which is what FastME is doing, would not. And as you add more noise, it gets worse, but our algorithm does pretty well. And we've tested this on a data set of jawed vertebrates, and it works well. But ultimately, we may be able to get the best routing on a balanced minimum evolution tree, but you could still do a better job perhaps by midpoint routing a RAXML tree.
So just to be clear, that last statement about routing was about like using FastME with a midpoint routing versus
Yes, exactly.
your algorithm.
Yeah, FastME with the midpoint routing versus estimating the root in balanced minimum evolution using our algorithm.
So okay, one thing I understand that your algorithm does deal with a rooted tree. On the other hand, BME is inherently an unrooted criterion.
Yeah. So
the connection between these.
Yeah, so we were able to prove in this paper that while BME is a fundamentally an unrooted algorithm, you can also just pretend that you add on another. So you take our rooted tree and you pretend that there is an extra taxon that is very far away from all other taxons, right? It's just sort of pretending it exists, right? And then if you unroot that tree is now unrooted, right? So you can take a rooted tree, add a distant ancestor to it, and then unroot it, and the rooted part will still be the same.
So we have our original data matrix.
Yeah.
We add an extra row in a column, which is some large number.
You don't even need to add. You don't actually need to add that extra row and column. We simply need to adjust our algorithm here, multiplying it by 0.5. It adds another edge in, basically. But we don't actually have to do any change of our data at all. And it's just conceptually, that's how we can move from balanced minimal evolution, which is unrooted, to a rooted tree by pretending that we have this extra edge that is distance from everything else. Because we're in balanced minimal evolution, we don't actually need to calculate this distance. We just need to assume that it exists. And then if your tree is ultrametric, very clock-alike, we can provably show that you can find the correct root. The issue here, of course, is that very few trees are actually clock-like, and very few data are actually clock-like. So, how useful this will be for applications, we don't know. But it works better than midpoint routing in this example, at least.
Cool, thanks.
So I'm going to pause for a reflection and then really breathe through some last bits, because I realize we don't have much time left, or maybe even skip the last bits. I don't know. But so reflection is the algorithm is powerful, but it's cubic, and that's not great. And fastme is really great most of the time. And so maybe tree search as it is pretty good, and maybe gradients are amazing, but perhaps what we have now is very good. So maybe the best application of this approach is exactly what Eric was saying before. You start with a RAXML tree, add some, convert that to phylogenetic, add some noise, calculate the gradient, and pick the best 10 directions of that gradient, evaluate that likelihood, and replace our algorithm for the standard balanced minimum evolution as a way of doing fast searches in RAXML. At the end of the day, balanced minimum evolution is going to be strongly correlated with maximum likelihood. And picking the best directions in our cubic algorithm will probably be fine. Few people will be using RAXML for more than 1,000 trees. For 1,000 trees, our algorithm will still be running in seconds. So maybe that's the best approach. But more broadly, where do we go with distance-based methods, right? I mean, are they always going to be relegated to the starting tree? We were able to make all this progress on the gradients simply because distance methods are simple. But likelihood approaches, I'm not going to say it's impossible, but it's going to be very difficult to sort of do all the steps that we did here for likelihood for topology. Super matrix approaches, maybe, they're still good, but there's a lot to be sort of thought about for distance methods. A lot of people are negative on them, but at the end of the day, they're consistent. And at the end of the day, if you have the true evolutionary distances, you get the correct tree. So maybe we should be using deep learning to compute better distances. And then from those better distances, I'm thinking of like that phyloforma tree, phylotransformer tree paper, with better distances, maybe we can get better trees. So for more information on this, the phylogenetic paper, which thanks to Matt and Neil, who's a co-author, co-first author with Matt on both these papers, was indispensable as well on these. The leaping paper is the one which introduces all the gradient steps. And then the inspiration for all of this came from a recently published branching paper in Journal of Mathematical Biology, which is totally different from all of this, but maybe gives you an understanding of why we went in this direction. So I think we're out of time for questions. I had some slides about Felsenstein's likelihood, but maybe that's for another day.
I don't know. I would love it if you would like at least.
Let me go through it. Let me go through it quickly. I can do it. I can do a quick one in 5 minutes. So, Desper and Gaskell had this seminal result where they assumed the variance was proportional to the sort of length of the tree in terms of its edges. And they found that balanced minimum evolution is the minimum variance estimator with a length equal to the weighted least squares estimator. And of course, neighbor joining is a heuristic solution from this. This is in a later paper. But of course, they had to assume that the variance was proportional to that path length. And that's an assumption that I feel was never fully justified. I mean, it's plausible, but it's quite a strong assumption, I think, right now. And I'd love to be told why I'm wrong there, but I think it's a strong assumption. So what we wanted to do was, well, how do we arrive at balanced minimum evolution or something close to it from Felsenstein's likelihood? So it's going to be a lot of maths here, but just ignore the maths. Look at the red boxes. Let us pretend that we take Felsenstein's likelihood for the unbelievable, impossible situation where we know all the internal character states and the external character states of the tree. So, we knew the sequence of the most recent common ancestor of human and chimps, for example. Now, when you do that, we end up with the likelihood that's, of course, easier than Felsenstein's to work with because we don't have to do with marginalization. And then after quite a lot of derivations, we end up with this sort of entropy type likelihood. So where the behavior is controlled by the likelihood of a single site. And, it was quite astounding for us to see this because, the approximation is, if we just look at the sort of leaf-to-leaf paths across Felsenstein's likelihood as the approximation, we can approximate this using balanced minimum evolution and least squares by putting the least squares times into balanced minimum evolution. But of course, we can't do this using our methodology. But what we can do is, take a prior on the branch lengths. And what we find is that, depending on the choice of this prior and like an exponential distribution with mean 1 over lambda, we can get back to balanced minimum evolution. Now, I think this is we're still working on this now, and this could, all subject to change. But this is a useful way of showing why balanced minimum evolution works with its connection to the more famous Felsenstein's likelihood, rather than looking at it from a weighted least squares perspective. And all of this has to do with looking at the entropy down a tree and an approximation of that. And so, if we can kind of make this work and, sort of explore this a little bit more, I think, it might go a long way to sort of telling people that distance-based methods aren't maybe as negative as they should be. But of course, more importantly from my goal would be, if we end up with an approximate likelihood on the scale of the true Felsenstein's likelihood, then we can use Hamiltonian Monte Carlo to do topology searching, which could be, very, very useful at that stage, because most of Bayesian phylogenetics is hamstrung by the fact that we have to take random walks. Using Hamiltonian Markov chain Monte Carlo, we can just leap through the posterior now and get a really nice sample of posterior trees, which we can then refine using other methods if we wanted to.
Would you mind going back one slide and I just want to understand this entropic likelihood a little bit better?
Yeah, maybe it's time for Matt to lead in.
Okay, I brought him on.
Yeah, so I guess essentially what it's doing is, because we treat every site independently when we're looking at the likelihoods, you can think about the long-term behavior. If you imagine you had kind of site after site after site that you were simulating, the long-term behavior of that likelihood is going to be dominated by the expectation of the likelihood of a single site that's being simulated. And so what you end up with is, because we're kind of assuming in this case that we're using all of the internal sites as well as the external sites, you can find that likelihood of a random site, the expectation of that, by just considering the expectation of the likelihood across like each individual branch. So if you've got just two nodes, which are say distance 1 apart, their contribution, the contribution from that edge, will just be what is the expected likelihood of your mutation chain if you start it at one node and then simulate it for time 1 and you take it to another node. And so that's kind of where this entropy comes in. And there's a few assumptions that go into it. You assume that the mutation process was started from stationarity at one node in the tree. And obviously, kind of this idealistic formula is still kind of based on the fact that you know these internal sites. But that's kind of the idea, if that makes sense. So it's all about, just looking at those edges individually.
Yeah, let's see. So, I mean, so maybe we can just phrase it in a generative way. So when I think of Feldenstein's likelihood, I think of like, I simulate starting at the root, I sample a sequence according to the stationary distribution, and then I simulate the sequences down to the tips, and it is the likelihood of generating that sequence alignment, or maybe let's just say a single site. So that single site simulating down that tree. Is it possible for you to explain what you have here in a generative sense in the same way?
Yeah, exactly. So, it really works in a very similar way. So you start with your root. And then, for example, if you've got like node X is directly joined to your root, we can think about the likelihood that's kind of associated with the edge between the root and node X as just the probability, the expected probability of seeing whatever the site on node X is and whatever the site on node R is. So like the probability of seeing that transition. Because everything's then in stationarity, if you want to choose another edge somewhere in your tree, rather than having to do some kind of long calculation where you do loads of conditioning on all the other states, the distribution of the sites on kind of some other nodes, node A and node B, is exactly the same as if you'd started at node A at stationarity and then simulated down to node B, as long as node B is further away from the root than node A. And so that's kind of how you build it up. Like this kind of long-term expectation effectively decouples all of the different evolutionary processes in the tree and lets you get this nice summation form.
Okay, and then so is it so can we think of it as like a likelihood where all these states, the internal node states, are adjoined onto our understanding of the sequences? Or is that, do we treat them as part of the data, or are you saying that basically we assume that every parent sequence is drawn from the stationary distribution and we're...
So you can still assume that kind of everything is joined from the root and you simulate downwards. But it's because, so effectively, you can write, if we maybe go back to the previous slide, the one before this one. So you see this formula PGU over this product. When we consider the logarithm of it, we're going to have, obviously, that product is going to turn into a sum. And now we can think of the site values, VI1 and VI2, as random variables. And so when we take the expectation of P of GU kind of over this randomly generated sequence, we only need to find the kind of expectation of the individual logarithmic terms, because we've just got a sum and it's going to split out. And so then you can show that VI, V2, kind of the distribution of that random site, is exactly the same distribution as if you'd started from VI1 and then simulated to VI2, just kind of by the Markov property and the stationarity of the whole thing. So that's where that comes from.
Yeah, it just makes, there's just one little thing that's missing. I understand all those things, but I just don't understand. We have actual sequence data at the tips and we don't. So then is it there? Yeah, I just don't know how we can consider that to be data.
Yeah, so I guess really what the power of this is that it shows us that even though we don't have the data on the internal nodes, that we can still kind of get this approximation to the likelihood. So the way that the data feeds into the model is we go from data to our estimated branch lengths, and then from our estimated branch lengths to the likelihood. So kind of the data will just be kind of one, if we've got loads and loads, we've got millions of sites of genetic data, we'll do one single step at the start where we go from that to a distance matrix. And then for each tree, we can go from a distance matrix to the times. And then if we were doing this discretely, we could go from the times to the likelihood. And so, sorry, Sam.
No, and then the crucial point there is there's a deep connection to balanced minimum evolution there. But I think Eric, where you're confused is you're thinking of Feldenstein's likelihood like you would implement it in RaxML, where you've got some tip data and you calculate a likelihood with respect to that data, right?
I am, but I think what the point that you're making is that this construction you're describing is taking us from the alignment to
this construction starts from something impossible that you could never actually calculate and you would never actually use to an approximation of that.
Right, which is the BME.
Which then gets you the BME. The whole point is that this more general likelihood it's impossible. You don't have that data. You never compute it. It is consistent. It has all the good properties of Felsenstein's and more. But you'd never compute it, right? You never even think about the data at this stage. But if we think about the branch lengths and the mutational process in this, and we sort of follow this to its, we sort of follow the logic behind this, create an approximation of it that is a tip-to-tip approximation, we end up with this entropy formula and then a connection that is very close to balanced minimum evolution in certain limits. Is a long story short.
Cool.
But I mean, we're early days in this. So the other ones, obviously we're still early days in the other ones. We haven't published them yet. But this one we're still working on. So if anyone is sort of interested or working on something similar, reach out to me and Matt, and we can chat about this.
Yeah, I look forward to that preprint coming out. I will read it.
Yeah. So final thing where the end is thanks to sort of Neil and David and Mark and Crystal, who are the other co-authors on all these various papers, and thanks to the phylogenetics community. It's a really warm and welcoming community. After working for years in public health, everyone you speak to in phylogenetics seems to be keen, interested, and nice, and it's very nice to interact with such people.
That's wonderful. I'm glad that it's felt welcoming. Thank you for your really interesting talk. I love having someone come in from the outside who with a whole bunch of new ideas. It's been exciting to watch. So I invite anyone to post questions if you have them. We just have a couple minutes.
And no worries if you don't have them now. You can always reach out to us later.
Yeah, it's interesting. I mean, we've been thinking about this notion of smoothness that you've been talking about, and it's interesting to think about. We want things to be. It feels a little bit like we want things to be intermediately smooth, right? Like we want to be able to make our way easily to the high posterior density region or the maximum likelihood tree or something like that. So yeah, it's interesting to think about what are the smoothness properties that we actually want in phylogenetics.
We essentially, accounting for rounding errors, we essentially want the ability to traverse a path between any set of trees and any other set of trees at any time, right? So if you get to a certain range of tree space in this continuous representation, and you can still get to another tree space, you don't need to be hamstrung by discrete changes on that tree. And that's, I think, where the power of the gradient really comes in. But of course, the sense of smoothness in terms of like if you did a Fallot-Vec type formulation and you do a discrete optimization on that, I really like the Fallot-Vec SPR because SPR has emerged as the way to traverse tree space, right? It's the porridge just right. Tree bisections too costly, and nearest neighbor interchange doesn't explore fast enough, and SPR is emerging as the sort of the winner. And the fact that Fallot-Vec has that property in there means it has the right smoothness for an operation that has been very well tested. But you get back to the BHV space or the slicing of high dimensional oranges, how we connect one tree to another tree in this whole space of other trees, and how you can get there in a nice way. I think that's the really powerful approach, so we don't get stuck places. You run an optimizer for long enough, you'll eventually find something very, very good. And I think if there's one contribution that I think I'm happy about with all of this is that while it is cubic, the gradient does allow you to take these nice steps.
But like you say, I mean, this is a cubic operation where each operation is pretty trivial. I mean, like if you're as soon as you're talking about trying lots of phylogenetic likelihood vectors, there's like the sequence length matters and all those sorts of things.
No, I mean, the cost of our operation is very cheap, and so the next stage for me is literally to try this in RaxML, and pick the best directions and see how well that does. That could be a nice way to land. And the other one is with our likelihood framework to try Hamiltonian Monte Carlo. Put this in Stan and just sample a bunch of balanced minimum evolution trees. It'll probably be a decent posterior, right? We'll probably be very close to Mr. Bayes, maybe.
Well, you know that Alexandros Stamatakis is in Crete right now and is trying to get people to come to Crete. So I recommend, if you're interested in doing approximately, you should go to Crete.
I wouldn't mind a trip to Crete. Maybe Matt and Neil would be quite happy about that as well.
Cool. All right. Well, I think that's what we have time for. Thank you very much. And this concludes our series on machine learning. The next one is going to be on birth death, and we're going to start with one of the people who started it all, Sally Otto from UBC. So that'll be exciting. All right. Thanks again, Phyllis.